Hello, everyone. Welcome to the Full Cup is Full Access webinar series, where you get to pick the subject and we bring in the industry experts to talk about them. And today, the subject is in-ear monitoring systems. And we brought in a couple industry experts here. I pull up my camera. Rick Murphy and Greg Simon from Sennheiser. And my name is Jim Ripp. I'm that guy at the bottom of the screen. You can see me live now. Just a few things before we get started here. We have some housekeeping issues we need to cover just real quick. There is a question and answer feature that's available to you all. If you go ahead and type in your questions during the webinar, I will present those to Rick and Greg at the end of the webinar, unless of course it's an urgent question. Well, of course we'll ask it right away. So go ahead, feel free to type in your questions, send them to me. I will then transfer them out to the guys. Recording of the presentation will be made available for everybody on YouTube's, and you will get, if you've attended or signed up at least, you will get a copy of it automatically. That way, if you have to duck out halfway through, you don't worry, you'll be able to watch the rest of it. And also, a quick survey at the end is 2 or 3 questions. That's where you get to choose the subjects for our future webinars. So let's move forward here with Greg. I'm going to bring both Rick and Greg up here online so that you can see them. And as they're logging in there we go. There's Rick. I'm going to take a quick scan over, Greg, over your bio here. I didn't put Rick's up because everybody's familiar with Rick. Rick's a old hat with Full Compass. He's done several webinars with us. But a quick review here. I see Berkeley College and an expert in RF. So the Global RF Expert Program. That's pretty cool. So I'm going to hand it over to you guys. Greg, feel free to talk about yourself, or better yet, let's have Rick talk about you.
Okay. That's always best when I talk about it. Hi, how are you, everybody? I hope you're all doing well and staying safe and healthy and happy and all that good stuff during this crazy time. It's our pleasure to be doing this for you today. Hopefully you know about Sennheiser. If you don't, I'll give you a brief rundown. This year marks our 75th year, our 75th anniversary of being in existence. And I think Greg and I look pretty good for our age, is all I'm saying. Thank you. And it all began in a little farmhouse outside of Hanover, Germany, where Fritz Sennheiser founded the company. And today we have Daniel and Andreas Sennheiser, who are the co-CEOs, and they are the grandsons of Fritz, the 3rd generation of Sennheisers running the company. And basically, with a multitude of products that we've created over the years, but they've all come down to 2 criteria that we base everything on, and that is sound quality and build quality. We want everything to sound amazing, as hopefully the best in the industry, and we want things to be built to last, and not just where you buy a product and it's going to work for a long time. We don't replace our gear very often. We are right now on our wireless systems. We are at G4. The G3, which we discontinued a couple years ago, was lasting for 8 or 9 years. And you can, if you travel the country like during normal times, Greg and I would, you might stop in a church or a school or business that has G2 running. So those things are probably 10 years old by now, and they still work. They're probably not supposed to because of frequency allocation and things like that, but they still do. So, so with that, wireless is also one of our very important topics at Sennheiser. It's the product line that we put a lot of time and effort and resources into. If you were to take the top 10 products that we sell by piece, wireless products are usually 7 out of the top 10 products that we have year after year. We are very popular in the wireless community, and because of that, we like doing things like this and educating the customers making sure they know the ins and outs and intricacies of wireless products, because we think we make a darn good product, best in the business. And an educated consumer is our biggest ally usually. So normally, under circumstances without pandemic viruses, we would be roaming the countryside conducting what we call RF academies, which are 6 to 8 hour long seminars in person that we give, not just going over the little things about RF, but digging deep into RF, and not just about our products, but about RF in general. And so we don't have the ability to do that right now, but we are doing things like this. And so my ask of you, and I know Jim already mentioned it, is make sure if you have a specific RF topic or any microphone topic or headphone topic that you would like to see a seminar on, please put that in the comments, because we would love to educate more and do more of things like this while we can. It's a perfect opportunity for us. So Greg over there, he went to Berkeley and he's an RF expert. I don't know what else I need to say. I mean, it's right there. But he's one of our business development managers for the Pro division, and he's an expert. So I'm just gonna let him take it away and handle the rest of it. All yours, Greg.
Thank you, Rick. All right, so I'm going to share my screen here. Show my screen.
Rick and I are going to duck out, and I'll be monitoring those questions again, everybody, during Greg's presentation here. So feel free to type those in.
Cool. Yeah, and of course we can. You guys can absolutely interrupt me if you have any questions. We can, try to answer them as we go. So let's talk a little bit about in-ear monitors. Like, what is a wireless in-ear system, right? So a wireless in-ear system, very similar to a wireless microphone system, but backwards, is a device that utilizes an electromagnetic carrier frequency to transport the audio instead of a cable, right? So instead of putting the signal through a cable, we are using an electromagnetic wave in order to send that across. So let's talk a little bit about how the signal kind of works from the basics. So first, we've got a transmitter, and in the in-ear monitor case, your rack mount device is that transmitter, opposite of your wireless microphones, where that would be the receiver. So your rack mount device is the transmitter. This is the device that takes that signal, superimposes it on top of the carrier wave, the electromagnetic wave, and this is called modulation. So it modulates the audio onto a carrier wave. Then we use the transmitting antenna as a launch pad to send that out across the air. We then have a receiving antenna on the other side, which picks up this signal. And then we have a receiver, which is essentially a demodulator. So it undoes what the transmitter does in order to get back to that original signal, right? So we basically encode the information on top of the carrier wave on one side, and then we decode it on the other side in order to get back our original signal as close as possible. So in order to kind of understand how this process works, you kind of know a little bit about waves, right? And when we talk about audio, there are two different types of waves being used. So first, there are mechanical waves. Now, these are waves that require a medium in order to move through. So sound waves are a type of mechanical wave. They require air or water or something else in order to travel across space. In outer space, where there is no medium, mechanical waves will not transmit at all. This also means mechanical waves move at the speed based on the medium that they're in. So for sound waves, obviously in the air, it's the speed of sound. In water, it has a different speed. Everything kind of moves at a specific speed. When we're talking about RF, we're talking about electromagnetic waves. So electromagnetic waves transmit energy in a different way. They actually vibrate particles, charged particles, and they move on top of an electromagnetic wave, or they move with an electromagnetic wave. Now, since these are independent of the medium that they're going through, not only can they travel through, outer space where there is no physical medium, but they also move at the speed of light or near the speed of light, no matter what frequency it's on. So there's basically no latency happening on the electromagnetic wave. Electromagnetic spectrum, is different than the audio spectrum or mechanical spectrum, encompasses a whole lot of stuff, right? So a lot of these things you've heard of it, obviously AM radio, FM radio, we're using RF, radio frequencies for wireless microphones, but even things like microwave ovens use RF or electromagnetic waves, radar. You actually have a electromagnetic receiver in your body, and those are your eyes, because light is an electromagnetic wave. It goes all the way up to X-rays and things like that. Wireless microphones and in-ear monitors tend to be regulated into certain areas of the spectrum. So the UHF spectrum, which is pretty much the only spectrum in-ear monitors are in at this time, and there's very specific reasons for that, is being used for in-ears. This is where we kind of lie them. And in the United States, that's going to be 470 megahertz up to 608 megahertz. That is what is available to be used. And the FCC, which is part of the government, has regulated that that's the available space for us to use for wireless microphones or in-ear monitors in the UHF spectrum. We used to have more than that, but over the years, the FCC has sold off pieces of that, and unfortunately for us audio guys, the telecom companies and the ISP companies have way deeper pockets, and so the only companies at this point that actually were able to buy spectrum in the US were companies like Verizon, AT&T, T-Mobile, Comcast, and they went for tens of billions of dollars in order to get a piece of that spectrum. So now we're regulated with everybody else to be using this UHF spectrum. There are a couple of other ranges that wireless microphones will use, like the 1.9 gigahertz and 2.4 and even 5 gigahertz. But due to latency, we do not use any of those for in-ear monitors. In some microphone situations, adding some latency is okay, depending on the situation, but in an in-ear monitor, it's not. We'll talk about that a little bit more as we kind of go through it. So here's a couple other things that when you're talking about any sort of wireless, whether it's a microphone or an in-ear, basically the same technology going on here, there's some important rules of thumb. So first thing to know is propagation. So the higher the frequency is, which has a shorter wavelength, the less penetration you're going to get. Whereas the opposite, the lower the frequency, the more penetration you're going to get. Meaning, if the lower the frequency is, the easier it can travel through obstacles like walls or, different obstacles that you may need to go around. Whereas the higher frequencies tend to not be able to penetrate through those solid surfaces as easily. On the flip side of that, there's also reflection. So the higher the frequency, because they're not going through these obstacles, they're actually reflecting off of the obstacles more easily, whereas the lower frequencies don't reflect quite as much. And depending on the situation, depending on the room, and depending on what you're trying to do, you may want more reflection, you may want more propagation through, obstacles. So just keep in mind, as the frequency goes up, you're going to get, more reflection and less penetration, and as the frequency goes down, you're going to get more penetration but less reflection. Another thing that's really, really important, especially when you're talking about in-ear monitors, is cable loss. This is actually the #1 place in a system that you will lose your energy, is through the cable. And all cables are created differently. Just because a cable is really thick doesn't mean that you're going to be low loss. And whenever you're designing a system that has something like a remote antenna, which we'll talk about here in a minute, you definitely want to make sure you take into account the cable length and the type of cable in order to make sure that you're getting the best possible signal. And it's all about getting to like a zero sum. You always want to get as close to zero as possible. So the least amount of loss or the most amount of loss or the most signal or the least signal, none of that is the best way to go. It's always about getting as close to unity gain as possible. Another thing that's really important is antenna length. So lower frequencies need longer antennas, and higher frequencies can use smaller antennas. So for example, in the UHF range, the antennas tend to be around the same size because that's not a huge frequency range. But when you start going up into like the 5 gigahertz range, those antennas are absolutely tiny. And then if we wanted to go down to a much lower frequency, like something in the VHF range, you need these gigantic antennas in order to pick up that signal well. And then the last thing that we want to make sure that we're talking about is in terms of range, the higher the frequency is, the less range you will get, assuming the same amount of power. So we have this little chart here that kind of shows you when you are at, like a 2.4 gigahertz system, you need almost 10 times the power in order to reach the same amount of distance as you would somewhere around 600 megahertz. So it is exponential, and as you go up in frequency, you need more and more power in order to get the same distance. All right, so let's talk a little bit about differences between the transmission of IEMs and microphone transmissions, and a couple of different things that we have kind of going on here. So first thing is pilot tone. So in a wireless microphone, we use pilot tone in order to send things like battery information and do some sort of safety kind of stuff. In a in-ear monitor, we actually use it to differentiate the difference between stereo and mono transmission. We also have, we need more signal to noise ratio if we are going to be doing stereo on an in-ear monitor. And both of these things are really because we're still regulated to 200 kilohertz of bandwidth. So a wireless microphone, which is always a mono source, has the ability to use up to 200 kilohertz of bandwidth of the spectrum. And this is a regulation that's set by the FCC, which is the US government, also the ETC, which is the same counterpart to the FCC, but in Europe. Both of them have agreed 200 kilohertz is the limit. When we use stereo in-ear monitors, we don't get 400 kilohertz, unfortunately. We still have to stay within that 200 kilohertz, even though now we're technically sending two signals across. So this is kind of why we need a higher signal to noise ratio, and we have to use that pilot tone to kind of differentiate, because we're still stuck in that same amount of bandwidth. And so, the receiver needs to know, hey, is this a stereo signal or is this a mono signal? Because I'm just seeing one chunk that's kind of popping across here. Also, in-ear monitors, because they're using a lot of that 200 kilohertz and there's a lot of energy happening there, it does require a higher safety margin when calculating intermodulation. So if you've got, when you're doing your intermodulation calculations, you always want to be more careful with in-ear monitors than traditional microphones. And it's really because you've got more data coming across in that stereo image. And the other thing to note is that if you do go with your mono signal versus a stereo signal, because you can use all of that energy in one spot versus splitting it between the two signals, you can actually get more range for, in a mono setting. So let's talk a little bit about, how to get the longest distance out of a system, right? So first, obviously, you want to be in that mono mode, and that's going to get you the most distance. Your antenna placement is going to be really important, right? So you want to get it up as high as possible, which we'll talk about a little bit more later. And then using a directional antenna will get you more forward gain. So in this case, we're using an A2003, which we'll talk about here in a minute. And kind of maximizing the range is kind of about picking each setting and each item in order to kind of maximize that range. So for example, we did a test with a 50 milliwatt transmitter outdoors, which is obviously most ideal, and we're using our A5000 with a very short cable, and we were able to get more than 1,000 feet of coverage with that. So you can definitely get a lot of coverage, but as you change what you're doing and what your requirements are, you kind of have pros and cons depending on what you're trying to do. Let's also talk a little bit about digital and in-ear wireless. So any digital system is going to add latency, right? So digital systems add latency because you have to convert it from the analog domain. So any audio source is going to be analog, right? That is going to need to be converted from that domain into digital, and that takes time. Then we send this digital information across the air, and that's on electromagnetic waves, so that doesn't really take any time. And then we have to now, convert it again on the other side back to analog, so you can put it through a headphone amp and listen to it, right? So this is always going to add latency. Some of the systems have gotten, as low as 2 milliseconds of latency. Most of them are 3 milliseconds of latency for wireless microphones. But for in-ears, we really don't do this because the latency can really mess with you on in-ears, right? So that's why we're still using, analog. So, if you're singing, for example, you're hearing yourself internally, and then you're also hearing yourself again with the in-ear monitor, right? And any delay there can really kind of mess with you. It can almost sound like phasing, and it makes it very, very difficult in order to perform. So even small amounts in this scenario, you can hear it, and it can kind of, mess with you a little bit. And this is kind of why it's so difficult to have latency inside of an in-ear monitor. And so digital in-ears at this time are really not recommended. We don't make any, and it's really because of the latency, right? The latency in a standard analog in-ear monitor system at this time is still near zero. We can probably measure it in microseconds. So, very, very imperceptible. Digital systems were in the, 3+ millisecond range. Also keep in mind that latency is cumulative, right? So if you're just using a digital in-ear and everything else in the system is analog, you might be able to be okay with that 2 to 3 milliseconds. But that's not usually the case, right? You usually have a microphone that might be a digital microphone adding 2 to 3 milliseconds, and your console is a digital console that could be adding another 3 or 4 milliseconds. You have a digital snake could be adding another couple milliseconds, and all of a sudden you're at 10 or 12 milliseconds. And if you ever had a pair of in-ear monitors in and you're trying to sing with 10 milliseconds of latency, it's almost impossible, right? So that's not ideal. And so for in-ears at this time, we don't recommend digital. And it's not, maybe in the future if the technology gets fast enough where we can lower it down, significantly under 1 millisecond, might be worth it. So let's talk a little bit about what system Sennheiser actually has available at this time. So Sennheiser makes 2 in-ear wireless systems, and they're actually pretty similar systems. So we have the IEM G4 system, which Rick was talking a little bit about how we're on our generation 4, which is the Evolution Wireless in-ear monitoring G4 system. And that system retails at $9.99, and that's going to include your receiver and your transmitter, and we also kind of throw in a free pair of in-ears, and we sell it as a little bit of bundle. The 3 really big points to this system that make it different than our 2000 series, which we'll talk about in a second, is you get up to 46 megahertz of bandwidth. Depending on which band you get, it's anywhere between 42 and 46 megahertz of bandwidth. And that gives you the ability to do quite a few channels. Depending on the environment, you can get up to 16 of these in a single band if you needed to. If it was pretty open, 8 you should be able to get pretty easily. And you get up to 50 milliwatts of output power, so you can get some significant range with this system. Also, it's got a really nice headphone amp on it, and it uses our top-of-the-line HDX companion. When we go over to the 2000 series, you're stepping up about 50% in terms of price per channel. We don't include the free in-ears at this point, but this is also sold in a piece-by-piece system, right? So we actually have a 2-channel transmitter. You can't actually buy 1 channel of 2000 series. So we got 2-channel transmitter, and then you buy body packs separately. It averages out to half of a 2-channel transmitter, and 1 body pack is approximately $1,500 retail. And the big advantages over the G4 system is we're going to give you more bandwidth. So you have up to 88 megahertz of bandwidth. So you get more channels, more opportunity to have a free open space. Because that spectrum is shrinking and everybody's sharing this smaller piece of spectrum, the more bandwidth you have, the more opportunity you have to find an open space. So obviously, having up to 88 really gives you a lot more opportunity to A, have many channels, and B, find an open spot in a really terrible space. And the other thing is we have up to 100 milliwatts of output power here. One really big caveat with that is the FCC does require you to get a license from them in order to use above 50 milliwatts. So if you are going to do 2000 series and you really need that 100 milliwatts for some extreme range, that's really where you'll need to get a license. In terms of the companion and the headphone amp, they're actually the same as the G4 series. So realistically, our G4 IEM is going to be the best sounding system on the market. 2000 series will have some more features, but will be equally good in terms of its sound quality. Comparison between the 2 of them, they should be pretty identical. They use the same companion, which is the just to go through it really quick, is the compression that we use in order to get that signal to enough dynamic range in order to send it across, and then the expansion on the other side to bring it back to our full dynamic range. All analog wireless systems, no matter who makes them, whether they're in-ears or microphones, use some sort of companionship. The big key here is making sure that it matches on both ends. This is also why technically you could use, a Sennheiser transmitter with a short receiver and vice versa, as long as you turn off some of those safety features. But because the compression and expansion doesn't match, it tends to sound really weird. So obviously we don't recommend doing that, but in a pinch you could make that work. So let's talk a little bit about the antennas. So the first antenna that we're going to talk about is going to be the quarter wave antenna. There's also half wave antennas available here that come with the units themselves. So these are going to be an omni pattern. They're going to not give you any sort of forward gain or extra range, but usually you can get pretty good performance out of these. And keep in mind they are omni, so you're going to get full 360 degrees around that antenna in terms of where the power transmits to. The next option, which tends to be one of the best inexpensive options for in-ear monitors, is a directional antenna, also called an LPDA. So what this is doing is this is now taking all that energy and focusing it in a single direction, right? So you're actually going to get 4 dB of forward gain. And just to put that in perspective, 6 dB of forward gain gets you about double the distance. So it gives you a significant increase in distance. It's also going to reject or not send as much energy out the back. So 10 dB less is going to come out the back of the antenna, which will also enable you to avoid sending that into a bunch of microsieverts or something like that. So it really kind of focuses where your energy is kind of going. And this allows you to also, kind of ignore some other unwanted interference sources. So this is our A2003. These are completely passive antennas, and these retail around $279. The other option is we have kind of our more professional version of the omni directional. So there's still going to be a zero gain here, but you get a much bigger, radiation pattern kind of coming out of this guy. So it's that same pattern that you're going to have on basically two sides here. So we still call it an omnidirectional, but you are going to get null points at the top and the bottom and the razor sides there. So you're going to get a lot of energy out of one side and another. So the best way to think of it is, two directional antennas kind of glued together, facing in different directions. This will enable you to put this in a location where I got to be somewhere in the middle and I need to have coverage all around me. But you're going to get a lot less range because you're now using that energy to go in every direction instead of focusing it in one direction. And this is also, a benefit if you have a space that can be super reflective, and you can kind of send it everywhere and use those reflections to kind of get you coverage in more spaces. And so these are also completely passive, retail around $189. The last antenna we're going to talk about is a circularly polarized antenna. So these are basically the big boy antennas. Most professional scenarios, this is the antenna you're going to see everywhere. This is going to give you 10 dB of forward gain, so you get a ton of extra range out of this antenna. It's also circularly polarized, so you actually have a winding inside of there, and what happens is the wave is actually going kind of in a spiral as it exits the antenna, and this is going to enable you. So now, no matter what orientation your body pack receiver is in, it will actually give you the full signal of it. If you are using a different type of antenna and you happen to be, out of phase with that with the polarization of the signal coming out, you'll lose a little bit of your signal. So this kind of eliminates that. It gives you far more range. And it's very, very directional. So kind of, think of this more as like a spotlight, whereas the A2003 is kind of like a flashlight, and the 1031, which is the omni antenna, is kind of like a light bulb, right? So obviously you're going to get more light where you point the flashlight than in a light bulb, and if you have a spotlight, you're going to get a lot more light in that one spot. So antenna position is also super important. In most scenarios, the higher you can get those antennas, the better radiation you're going to get and the less stuff that's going to be in the way, specifically people in the way that's going to kind of block it. So we actually, on this particular scenario here on the left, we've got an A2003 there with a 50 milliwatt system, and we've actually, you can't really see it in the photo, but on that building on the far end there's a receiver, and we were transmitting across that space, many hundreds of feet. I don't know what the distance was. And then also here on the right, we've actually got a picture here. We were backstage with Cirque du Soleil, and you can see that A5000 is what they're using. They have quite a few of them, so they actually got this one pointed at the backstage, so no matter where they are on the backstage, they have their in-ears, and then they have another one facing across the stage, so they can actually get full coverage no matter where they are on that huge stage that they usually use that takes up the whole arena. And obviously higher is better. So let's talk a little bit about mixes and how many different mixes you can get, right? So each transmitter, which is your rack mount device in the IEM, is capable of doing either one mono mix or one stereo mix, and there's a couple other modes that we'll talk about here. So in order to do this, you're going to need auxiliary, outputs on whatever mixer that you're using, right? So if you want to have 8 stereo mixes that are all different, you need to make sure that your console has 16 auxiliary sends on it. That's usually a limit that a lot of people run into. So they'll buy 10 of these units, and then their console only has 4 auxes, and it's going to limit them. So just keep in mind that you're going to need an aux for every send. So if you're doing mono mixes, you can do 1 aux per. If you're doing stereo mixes, you're going to need 2 auxes per. So definitely something to keep in mind. The other question we get a lot of is, how many body packs can I have with a single transmitter? And the answer there is you can have as many as you want. So the best way to think about this is like your own MIDI radio station, right? So if you're in your car and you tune into the radio, it's not, oh, there's already 5 other people tuned into that radio station, you can't tune into it, right? The energy is going everywhere, and as long as you're able to receive that energy and tune into it, you can pick up that body pack. So, theoretically, you can have one transmitter going to hundreds and hundreds of body packs, and it would be no problem. The one thing to keep in mind is obviously everybody's going to get the exact same signal. So obviously, if you buy one transmitter and 10 body packs, you've got one mix there that they're able to listen into. So let's talk a little bit about the different modes that are available for in-ear monitors. So the first mode, which is the most common mode that you're going to get on in-ear monitors, is your stereo transmit mode, right? So you've got 2 inputs on your transmitter, which is your rack mount device, and you're going to use the first input as your left music, right input as your right music, or whatever the source is. Send that across the air, and then your body pack is going to be able to pick up that stereo imaging. Obviously, your left and right headphones will get left and right signal, and you get that really nice stereo image. You obviously get the least amount of range this way, but you still, in most scenarios, get plenty of range, and you can get that full stereo image. The other way to do this is to only use one of those inputs, put the device into a mono mode, and then you're going to have your volume control on your body pack, and you're just going to get that mono image. Big advantage here is obviously you're using half the amount of auxiliaries on your console, and you can get far more range because you're in a mono mode, so using all that energy for one signal instead of 2. So that's the advantage to mono. Obviously, the disadvantage is the stereo image is very nice, and it gives you a lot more space in the sound field. So you have to kind of pick which is better depending on the scenario that you're in. The last mode is something called focus mode. And what this is essentially doing is it's using that stereo availability, those 2 different channels, as a kind of, mix capability. So what is going to happen here is you're going to get, when you're in the focus mode, you're going to get a mono source, right? So it's going to be mono, it's going to be coming out both headphones, and then you're going to have 2 signals going in. And what's going to happen is it's going to put, the one signal on the top, instead of left and right, it's going to put it top and bottom. And then you can use that control on the body pack to blend between those 2 sources. So you can do a mix of the band, and you can have the vocal. And then the vocalists can turn themselves up and down as they see fit, right? This also allows you to kind of have, or you can do 2 different mixes, one that's more guitar heavy, one that's more bass heavy. Give the same mix to the bass and the guitar and let them kind of blend back and forth between the ones that they like better, to kind of do it that way. And obviously you have your mono system. This is also kind of a way to get 2 mono mixes out of one stereo transmitter. Obviously, you're going to get the same range here as you would from a stereo, even though you're running 2 mono sources, but you're still using all that energy for 2 signals instead of 1. But it gives you some flexibility to be able to kind of, change around what you're doing and allow the artist to have some control over their own mix. There's also one other mode that we like to talk about in the in-ear monitors, and this is called engineer mode. And so essentially when you put the body pack into engineer mode, and you do need to kind of go deep into the advanced menu in order to set this up, but when you go into that menu, you can set it into engineer mode. What it then allows you to do as the engineer is it allows you to sync the body pack to 4 different transmitters, right? So let's say you're the engineer, you've got 4 different mixes up on the stage. You can sync it to each one, and then you can toggle through those profiles so you can jump back and forth listening to what each of your artists up on the stage is listening to. And it not only will set the frequency, but it also does the name and any other settings they might have on their body pack, right? So if they've got like a low cut filter and you're adding tons of bass, and they're like, I don't hear any bass, and you've got it cranked, well, it could be because of that. So when you're the engineer, you can flip between these different modes and kind of jump back and forth, tuning to each different transmitter very, very quickly. So it's a really cool advantage that we have on actually all of the systems that are available. So the next thing we're going to go into is intermodulation, right? And when you're setting up any sort of wireless system, especially in your monitors, calculating this intermodulation is really important. So what is intermodulation? Intermodulation is when 2 signals are applied to an electronic circuit in a nonlinear fashion, and it overloads that circuit, right? So essentially what happens is you get 2 transmitters near each other. All antennas can either transmit or receive. There's no such thing as a receive or transmit antenna. They both do this. They all do both. So what happens is the energy from one antenna goes up into the other antenna, and then it overloads the transmitter on the other side of the antenna. And then what happens is from this overload, it generates harmonics. And those harmonics can become, they do become new frequencies. And these come in different orders. So you'll have, second order, third order, fourth order, fifth order, sixth order, seventh order. As you go up, they get less and less important because they're less and less powerful. But we have to be careful especially about the third and the fifth order harmonics, because the way that the math works, they end up just above and below your other frequencies that you have. So for example, if you have one transmitter at 500 and you have another transmitter at 501, sorry, when they overload each other, you're going to get these new harmonics that show up at 499 and 502. You're going to get other ones that are a little bit lower power that are 498 and 503. And now these frequencies can't be used. If you use that frequency for another microphone, let's say you set your first one at 500, your second one at 501, third one at 502, that 502 is going to get interfered with by those harmonic frequencies that have just popped up. So we need to actually calculate out all of these frequencies. The second and fourth order, really, we don't care because they're actually multiples of the original frequencies. So they end up in frequency ranges that we don't have microphones in. So we're not super worried about where those are falling. But the third and fifth order can, destroy the sound from other systems, in our system. So here's a little bit of an example of what it kind of looks like on a spectrum analyzer. So this is 2 transmitters 3 feet apart, and you can actually see those third order harmonics are pretty loud. Those would be plenty loud enough to interfere with another signal. And then you got those little tiny, bumps there on the right. Those are actually our 5th order harmonics. If we move those transmitters a little bit closer together, so that's 1 foot, now all of a sudden the 5th and third order harmonics become much louder, and the 5th order, are now becoming interference frequencies. So we got to be really careful and make sure when we do these systems, we calculate out this kind of stuff. So on any of our systems, when you do those scans, it again has the banks and channels. What that is doing is those are pre-calculated frequencies where the intermodulation won't fall on top of other frequencies inside that bank. And that's really what it's doing. It's kind of giving you the opportunity to say, all right, if I use these frequencies, even if I do get them close together and this intermodulation pops up, I can kind of avoid some of these other frequencies. So that's why when you kind of do this, when you have an antenna farm and you've got all your in-ears right next to each other, because these are all the transmitters transmitting the energy right into one another, is this okay, right? And of course, this is, based on what we just said, this is not a good idea. So here's a little bit of an example of something that we saw. And the thing to keep in mind is when you get enough energy and when they're close enough together. So these are, some IEM systems from another manufacturer. And the fact that it's another manufacturer is kind of irrelevant. All systems will do this. But these are very high power. These are 250 milliwatt transmitters. And antennas are all just sitting about 3 or 4 inches apart from each other. So there is so much overload happening in this system that when we did a scan, this is what we found. And keep in mind, this scan here is actually all the way from 470 all the way up to 714, because our 6000 series, that's what it can do. In the US, you only get up to that 608 range. So in this scenario, those 8 systems are essentially making the entire UHF spectrum unusable, right? So we turned just those 8 microphones off, or not microphones, in-ear monitors off, and then all of a sudden our spectrum looks like this, right? So if we have all those systems next to each other and they're overloading each other, not only do they generate all these harmonics, but they actually increase the entire noise floor, making it almost impossible. In that scenario there, you probably couldn't use a single wireless microphone in addition to that. So you've got your 8 in-ears and that's it. Nothing else in the space can be used. So this is where we have to start, worrying and coming up with other solutions of, well, what do we do if we need more than 2 in-ear monitors, or if we need higher power, or if we need anything, right? So here's another scan of these are all in a rack. Let's pretend they're in a rack here, and they're about 10 inches apart, right, when they're next to each other. Obviously, some of these will probably be below the other ones, which make them even closer together. And on a spectrum analyzer, you'll see you got your 4 carrier frequencies that are your main frequencies, and then you get all these other ones that are popping up, which start to become unusable frequencies and taking up a lot of the spectrum. This is also why when we're doing in-ear monitors, we want to make sure, along with wireless microphones, we want to make sure that we separate them out a little bit. So when we do have some of this intermodulation happening, even if we do some stuff to eliminate it, which we'll talk about here in a minute, that we kind of keep them about 8 megahertz apart from each other, right? So any intermod that will pop up tends to be right above and below. So if you keep them 8 megahertz in 8 megahertz chunks and you keep them about 8 megahertz apart, they usually don't step on each other, and we usually recommend that you do a little bit higher frequency for the wireless in-ears, and then you can go a little bit lower in frequency for your body packs, and this will help with some more reliable operation. This is also where we start talking about, well, what do we do to start to get rid of some of this intermodulation? Like, how can we get around this? And this is where active combiners come in. So active combiners are specifically used for in-ear monitoring systems. You'll get no attenuation out of an active combiner. So if you put, 4 50 milliwatt carriers in, you'll get 4 50 milliwatt carriers out, but they'll all be coming out they'll be isolated from each other, and they'll all be coming out of a single antenna. One thing to really keep in mind when using an active combiner, the amount of power that these combiners can handle is very important. You never want to put too much power, more power than it can handle inside of it. So you'll overload it, and if you overload it enough, it can actually overheat. This is also why you never plug a combiner into a combiner. So you cannot daisy chain combiners ever. If you are lucky, it will generate so much intermodulation and so much distortion that you won't be able to use any wireless microphones. If you are not lucky, it will burst in flames. So we highly recommend that you never plug a combiner into another combiner. There's pretty much no scenario where it's going to work out. Again, if you learned one thing today, that's it, please. So let's talk about the couple of different combiner options that we have. So at the moment we have 2 different combiner options. We have a 4-channel and an 8-channel. So the AC41 is our 4-channel, retails for about $749, and this can handle up to 50 milliwatts per channel. So it can handle the maximum output of our G4 system. It can handle most of the output of our 2000 system, but it cannot handle the highest output power of the 2000. Again, if you're doing 2000 and you are doing 100 milliwatt, don't use the AC41, and remember, you're going to need a license. The other option is we have the AC3200. Now, this is an 8-channel combiner, and it also can do up to 250 milliwatts per input. So a lot of times we get the question, why is the 8-channel one so much more expensive than the 4-channel one? I mean, it's not double the price, it's not even triple the price, it's even more than that, right? So the thing to keep in mind is that each input requires exponentially more power handling. So a 2-input combiner requires a certain amount of power handling. A 3-input combiner requires double that power handling. A 4-input combiner requires double that. So an 8-channel actually requires 16 times the amount of power handling than a 4-channel does. So we need to be, able to get rid of a lot more heat. The amplifier inside of it needs to be far more powerful in order to do it. Additionally, not only is this doing 8 channels versus the 4 channels of the AC41, but it's also able to handle 250 milliwatts per channel. So now we've got 16, and we're adding 5 times the amount of power per, again, and it's exponential. So AC3200 can handle a lot more. This is also where we're really going to start talking about 4-channel and 8-channel combiners are really it. You theoretically can get a 16 or a 32-channel combiner, but the price would be exponentially higher again, right? So all of a sudden, if the price of a AC3200 is a little bit more than 4 times or 5 times the price of an AC41, the 16-channel variant of this would be, about 5 times the price, and all of a sudden we're at $20,000 for a 16-channel in-ear monitoring system, and it doesn't become a viable product. We actually have at our facility in Germany for testing purposes only. It's not something that we actually make as a product, but when we made one, it's able to handle 250 milliwatts times 16 channels, and the cost of it was over $20,000 just to build. So it's not something that we really do. So somebody says, well, but I need more than 8 channels, what do I do? So this is when you start using multiple combiners. You don't plug them into each other, but we start doing multiple systems. So let's just go through really quickly, how you kind of do this. So all 4 of these in-ear monitor transmitters will get plugged into our combiner, and then you plug a single antenna. At this point, we usually recommend doing a better antenna than the one that comes with it in order to really get you the best possible range out of the system. 8-channel combiner, same thing. You can get 8 channels in, 1 antenna comes out, and that transmits out the system there. And here we're showing our 2000 series, but you can, again, you can use the G4s with the 8-channel if you'd like. You can also use the 2000 series with the 4-channel, but you can't use the 100 milliwatts output power. If you're doing, let's say, 16 channels, you have a couple of options. You can basically divide it up into small individual systems, right? So for this scenario, I'm using the G4 systems, and we have the AC41s. And so in this scenario, you've got, basically 4 individual systems that are completely separate from each other, not plugged into each other in any way. And so we've got 4 G4s, we have an AC41, and we have a single antenna. Up top, it's just showing you the options. You pick one of those antennas, and then we just do that times 4. In this scenario, what we want to make sure what we do is we put those antennas, as far apart as we can. They don't need to be 100 feet apart or anything crazy, but definitely try to get them more than 3 to 6 feet apart from each other so they don't come back and overload the system on the other side. Also, we can do a 16-channel system with the AC3200s, right? So in this scenario, we only need 2 antennas because we're only using 2 AC3200s. And then we've got 8 of the G4 systems here, but you could also turn those into 2000 series into each one. And then we have 1 antenna per AC3200, and that gets you your 16 channels. So this is usually what we recommend. It's actually very, very simple. Usually when people say to me, well, how can I plug them into each other? How do I? The answer is just don't do it. You can have them separate, and having a couple of antennas is usually okay. If you do need to have a single antenna for some very, very specific reason, obviously if you want an active combiner, it's going to be extremely expensive and custom built. So that's option number 1. Option number 2 is starting to get into some passive options. That does cause other issues. It does cause a significant amount of loss. And so obviously if you do get a scenario where you need that, please reach out to us and we can do some of the math for you and kind of get it figured out. So with that said, that's kind of what we have here, but I'm going to kind of go through a little bit of a summary and just kind of sum up what we kind of talked about today. And then if you guys have any questions, I would love to answer them for you. So in-ear wireless monitors are great. They open up an entire new level of performance. They allow you to reduce stage volumes and save hearing, and really get to tune in. I very, very few times have I heard an artist who had the experience of using good in-ear monitor system tell me they want to go back to using floor wedges. So it's definitely an amazing upgrade in terms of your ability to perform and save yourself and be on stage. The bandwidth determines how many systems you can run. So if you're in a super crowded space, if you have lots of bandwidth, you can usually get a few systems. If you don't have a lot of bandwidth, it might all be blocked and you might not be able to get any systems. So whenever you buy a system, definitely check about how much bandwidth you're getting for the money. Also, more power can give you more range, but more power also gives you more intermodulation and more things you have to avoid and more noise floor. So we always recommend with pretty much any system, always use the least amount of power that you need. If you're going to get enough range with 10 milliwatts of output power, use 10 milliwatts of output power. Causes a lot less issues, a lot less intermod, a lot less noise. And if it gives you enough range, then it's good enough. If you need more than that, then bump up one setting to maybe the 30 milliwatt setting and see if you get enough range there. Only use that 50 or 100 milliwatt setting if you have to. So that's really, one important thing to always keep in mind. And that goes for wireless microphones as well. It's the same concept. The more energy you have in the air, the more issues you're going to have. Obviously, though, you can get more range that way. Always make sure you're calculating those intermodulation frequencies. The receivers, the bodypack receivers will do this calculation for you. We have our wireless systems manager software, which can do this calculation for you as well. And if it's a very complex system, you can always contact us at Sennheiser, and we're happy to help you with coordination. Antenna type and the placement of the antenna can make huge differences in the performance of a system, right? So if you're like, oh man, like I'm not getting enough range, but I don't want to use so much power, adding a directional antenna can get you a significant amount more range. And now all of a sudden with 10 milliwatts, you might have plenty of range. Get that antenna up high and use a directional antenna, and all of a sudden, all of your problems will go away. So that's definitely a good thing to do. Second to last thing I have here is multi-channel systems use active combiners in order to avoid that intermodulation and isolate from each other. And the most important thing is never plug a combiner into a combiner. They're essentially power amplifiers, and you never want to plug two power amplifiers into each other. So that's everything I have here for this presentation. And if there are any questions, I'd be happy to kind of go through it for you guys.
Oh, thanks so much, Greg. We're going to bring us all back up online here. I do have actually a statement. First off, the focus mode, outstanding. That is really cool to be able to do that as a vocalist. May I suggest that you add another knob on there that anybody can turn the guitar player down. So,
well, just don't send the guitar player into the mix and you'll be fine.
All right. So, all that aside, we've got some questions coming in. I know you mentioned that the placement of the antenna is very important to get it up high. In dealing in a stage situation or house of worship, anything like that, do you suggest, is there placement that's better than another? In front of the stage, side stage, does that make a difference? If back to front of house where they control it is?
So theoretically, it doesn't make a difference, right? It's really all about what obstacles that the energy will have to go through, and the distance, right? So if being on the side of the stage will get you closer, you can maybe use some less power. But if there's tons of obstacles on the side of the stage that don't allow you, that are going to block the energy, then maybe it's not a better solution, right? Also, sometimes front of house is 50 feet away, sometimes it's 300 feet away, right? So those are all things that are very important to keep in mind. Another thing when considering whether to put it side of stage or front of house is going to be your cable lengths, right? So as I said in the beginning, we didn't really talk about this too much. Your cable is where you're going to lose the most energy. You actually lose far more energy over the cable than you do over the air. So if you're going to say, well, if I put the antennas on side of stage, I'm going to be 10 feet closer or 20 feet closer, but then that means I have to run 100 feet of cable. You're going to lose far more energy there than you would if you just did them at front of house, right? So it's really all a matter of where, you know, where the receivers are going to live, or where the transmitters are going to live rather, and how long those cables need to be. And it's about trying to get to that zero gain, right? So if we said, well, you know, they're perfect position at side of stage, but I'm going to lose 20 dB in my cable, you're better off putting them at front of house, right? So my old boss used to say, the answer to that question is always it depends, and it's going to be based on you know, a lot of different variables. Again, you know, we're always here to help with those scenarios. So if you do have questions, hey, I'm thinking about putting them at side of stage, I'm thinking about putting them at front of house, we can always help with that. And the big things are going to be, well, how long is the cable run going to be? Where are the transmitters going to live? And how much closer will the antennas be when you do that, right? And then we can calculate that out. So if we're only losing an extra 1 dB on the cable, but we get the antennas twice as close, then that would probably be a better solution.
If I could speak to that too, in pro situations, generally you have a monitor world that's on the side of the stage, where a monitor engineer with, you know, he's listening to the musician screaming at him, telling him, you know, I need more of this, I need less of this, turn the guitarist down, things like that. And so his mixer is right there, so it makes sense to have the in-ears right there. It also makes sense at that point to lower the wattage on the output. So they can use the 10 milliwatts because they only have to shoot, you know, 20 feet to where the musician is. But also that gives you another advantage. You know, we are essentially bags of mostly water here, and a front of house antenna has to go through me to get to my pack if it's on the back, you know, in the small of my back. Whereas on the side, it could see it a lot easier. So that's another thing to sort of reconcile with. I've seen situations where amateur bands have had the mixer on the stage, like right by the drummer, and you know, maybe you use an omni antenna for that, so it can hit all the sides. But generally, the closer you are to the musicians, less power you need, the better the line of sight between the antenna and the receiver. So there's, again, like Greg said, it depends, but there's generally practices that pros use, and for good reason. So
and also Rick brings up a really good point. So we were talking in the presentation here about, you know, frequencies and obstacles and going through that. Don't forget, people are obstacles, right? And they tend to be, you know, pretty thick obstacles and with a lot of water in them, which blocks a lot of RF energy. And so, yeah, that's totally right. Like if it's on the side of the stage, it might be pointing at your back where the in-ear monitor receiver is. Whereas if it's in front of house, it has to go completely through you if it's on your back. If it's on the front of your belt, then maybe not, right? So it'll depend. Obviously, in that situation, most of the time you have it on the back so people don't see it. But, you know, line of sight makes a big difference. And if you don't have to go through the obstacle that is the person, you'll get a lot more, you'll be able to use a lot less energy, or you get a lot more energy to the body pack.
Excellent. Greg, real quick question. It's actually not a question. It's someone asking how they can get a hold of you. So what's your email, Greg, if you don't mind?
Well, I'll go ahead and put it in the chat here. Is that?
That works. Perfect.
Do that.
So we have a question from Zeke here while you're doing that. How to use 2 antennas with 1 combiner system?
So you're talking about multi-zones at that point. So that kind of gets into a little bit more of a complex scenario. And what you're going to really need to do is you're going to need to, you know, split that signal using a splitter. Usually you're going to use a passive splitter, and you're going to get a significant amount of energy loss doing it that way. There are splitters that will split it in, you know, different ways than just 50-50, so if you have a small space and a large space. And again, in those scenarios, when you're talking about multi-zones, we highly recommend that you get in touch with us. The proper way to do it is to use an active zone combiner. We have a product called the ACA3 that does that, and it does 4 different zones, but those can get very expensive. I want to say that retails somewhere around $5,000 because, you know, there's a lot of components that kind of go into that. You can do it passively. But a lot of times, depending on the scenario, you want to try to do it without splitting that signal and getting all that cable loss. So maybe a different antenna or an omni antenna might get you there. Obviously, if you're saying, well, I know I got 2 separate rooms that are in different directions that are completely blocked, then you can use some sort of passive splitting system in order to do that. And we can go through that on a one-on-one basis, because it will get quite more complicated. So I'm typing my email address in here, though I don't know. Let me know if everybody's seeing this. If not, obviously we can get it easier. Though my email address is really easy. It's just my name with a dot in the middle at Sennheiser.com. Rick's is actually the same as well. So just Greg.Simon at Sennheiser.com.
Well, but they've made mine Richard.Murphy, which is the only, yeah. Other than that, they didn't ask me what I wanted on my email address.
There you go.
So I think that went to the organizers and panelists only, though. So it might, I don't know if it went out to the
It's a selection for everyone in my.
All right,
okay.
I sent it out to everybody.
There you go.
Okay.
Awesome.
So again, another question from Zeke, and Zeke, correct me if I'm wrong, but this, I think you're referring to your cable questions that you had to talk more about cables, long, short. But his question is, how do you calculate loss?
So every manufacturer of the cables have that information. So there's actually a few tools online. There's actually an iOS app called RF Toolbox. But essentially what you're going to do is say, okay, I've decided that I might want to use times microwave LMR 400. Right? You can use that cable, and that will have a certain specification. So you can actually put in at 500 megahertz, at 100 feet, I'm going to get X amount of dB of loss. So that's actually the manufacturer of the cable that will give you that information. The RF Toolbox, I believe, just has maybe 20 random manufacturers or popular manufacturers in there with most of their most popular cable as an easy tool, but that's going to be the manufacturer of the cable. For an example, if you're using the RG59, which is your most common unlabeled, inexpensive RF cable, 100 feet of cable is going to get you somewhere around 20 dB of loss. Anything more than 6 is not advisable for a system in order to get good performance. So, we really recommend that you kind of take a look at that. And always, the shorter the cable you can use in an in-ear system, the better performance you're going to get, right? Because you don't really have any additional gain happening in an in-ear system. You don't want to use boosters or anything like that to compensate. So obviously, we can get a really short cable. That's going to give you almost no loss, and then you'll get the full forward gain of whatever antenna you're going to be putting through.
And also to note, because some people may not realize this, but antenna loss is not the same as, even though it's measured in decibels, it's not sound. So it's the quality of sound getting to and from the antenna. So it's not going to make it louder if you use better cable, or worse cable. It's not going to get softer. It's just a matter of how well is the transmission going to be. So that's important to note too. That's
how far that signal will get.
Right, and an antenna booster doesn't help that. Antenna boosters are only for very long cable runs that you can't use a better cable for some reason, or an active antenna or something along those lines. So it doesn't make it louder. It doesn't make your wireless work better. It just improves the signal going down the cable.
Yeah, and actually we've seen a lot of scenarios where people are like, well, the boosters, I can afford it, so I'm just going to buy a booster because it'll give me more, and it'll actually overload the output of the antenna and give you all sorts of other issues. So
yeah,
9 out of 10 situations, boosters are not the answer. And also keep in mind, even if a booster is the answer because you have to use a very long cable, it is going to increase the noise floor by whatever that booster is doing. So it may be getting you up and over that cable, but it's going to increase the noise. So boosters are always a last resort, and only use them when you have to.
Good point. Speaking of antennas, we have a really wide variety of listeners and audience today. So if you could, Greg or Rick, either one, explain what you mentioned: quarter wave and half wave antennas. What is that difference? What does that mean?
So actually, the difference there is actually the size of the wavelength, right? So if you have a electromagnetic wave that's around 300 megahertz, it's about a meter long. So in order to reliably pick up that signal, you want to have some sort of division of that. So a half wave antenna would be half of a meter antenna long, so something like 20 inches long, and that will give you good reception. You can also use a quarter wave antenna, which will be something like 10 inches long. Won't give you quite as good reception, but obviously it's a lot less expensive to build. It's a lot easier to kind of manufacture. So anything that's going to be included with an in-ear system is usually a quarter wave antenna. Only like the highest end systems will give you half wave antennas included with them. And again, if you're really using a higher end system and you really need a better antenna, we really recommend going with, a full size, Omni or directional antenna over that anyway. So we don't really include a lot of half wave antennas, but it's literally the center wavelength. So 300 megahertz is that meter long, and so you're either half or a quarter of that. All of our systems, because of the FCC regulations, are between 470 and 608. So now you're down, that quarter wavelength is in that like 5-inch type range. A half wave would be 10 to 11-inch range, being at the center point there.
Okay. Another interesting question here, and I've experienced this myself. And I guess this is general to in-ear monitor systems. If you're used to regular monitors, stage monitors, floor monitors, and you go with the in-ears, it's a big difference. It removes you from the audience. Do you have any tips or tricks to make the performer or the speaker less separated from the audience and less isolated?
So there's a couple of things you can do. This doesn't really have to do with the systems themselves. It really has to do with what you're adding to the mix, right? So I know some pro engineers that will actually have some audience mics and add those into the mix so people feel like they can hear the audience a little bit. I know that there's another manufacturer that started to make a binaural system, and so what that's actually doing is taking you from stereo. It's still using the 2 channels, right? So you'd still do it with the G4 or 2000 series, but then what it's doing is it's actually rendering the audio in binaural. So you're going from 2 channels to a full 360 degrees using the 2 channels. That gives you a lot more feeling of space. Makes you feel a lot less closed in. So that's a really cool option. One thing I will say about that, I've talked to a lot of pro engineers about this. Half of them say it's the greatest thing ever to happen in your monitors. The other half say they absolutely hate it. So it's really going to be dependent on the artist and what they like and don't like. But that's definitely a really cool innovation. And all it's really doing is it's allowing you to send your signals into that, and instead of rendering it in stereo, it's rendering it binaural, and then you have 2 channels going to your in-ear monitoring system.
Okay, another question here. Can this IEM be hooked up to a hearback system?
Yeah, I mean you can, and with the hearback system is essentially a private mixer for each individual user, right? Again, it's not a Sennheiser product, but what it's allowing the user to do is, instead of the mix engineer making a mix for, let's say, the guitar player, he's sending all the channels to the little mixer in front of the guitar player and allowing him to make his own mix. You could, at that point, take that hearback device, plug it into the wireless system, and then it will wirelessly transmit that signal across to his body pack. So yeah, absolutely. All that's doing is taking the control away from the engineer and giving it to the artist on what is going into the mix, but the wireless system isn't changed in that scenario.
Another question here is from David. Can you plug the paddle antennas directly into the transmitter?
Yeah, I mean you can, but you only have one, right? So you can only plug one paddle antenna into one system, and that's it. So if you do just need a single channel and you just really need a lot more range by getting a directional antenna, you absolutely can do that. Most scenarios, so you can take multiple systems and put them together through an active combiner. But yeah, absolutely, you can do that.
There's actually situations that you can take our transmitter from the in-ear system and a receiver from any of our Evolution wireless systems and do like a wireless speaker or delay line type of situation. And that's when a perfect situation when you would need to put a paddle antenna on that transmitter. So yeah, absolutely.
One other thing that to keep in mind is we did talk a lot about passive antennas. You never want to use an active antenna for an in-ear monitoring system. So an active antenna is essentially a passive antenna with a booster glued onto it, right? And what they're designed to do is the signal coming in from a wireless microphone goes into the antenna, goes into the booster, and then because the cable is so long, you're going to need extra power to push it across. When using it for an in-ear, it's right at the antenna, so all it's going to do is lose a lot of signal all along the long cable, hit the booster, and then distort the antenna. So definitely do not use active antennas for in-ear monitoring systems. If you happen to have an active antenna, just make sure that booster is off.
And that is pretty much it for the questions. I don't know if you guys have any last statements at all, or
Rick?
last tips or tricks.
No, I mean, I think like Jim said, it's when you have gone from a wedge to an in-ear monitor, it's a completely different world, and it may take a little while to get used to. One other tip that rarely gets mentioned, but never say, I want to hear the audience, so you take one ear out. Don't do that. You can actually mess up your hearing doing that. You can cause tinnitus in your other ear. So and you also usually end up bumping up your pack to compensate. Now you're overloading your what was once a good eardrum. So don't do that. But again, if you have any ideas for any types of seminars like this that we can do with Full Compass, please let Jim or I or Greg even, I don't care, let all of us know, because we need to know these things. We want to educate you. We want to make sure that you've got all the tools that you need at your disposal to make all the good decisions and make your mixes better and so forth. So thank you so much for coming out, all of you. Appreciate it.
Yes, thank you both, Greg and Rick. And I'll give you my email address, everybody, in case those who are watching the recorded version, they can't see Greg's email typed in there. But go ahead and contact me. My email is jripp@fullcompass.com. You can contact me, and I can feed this through to either Rick or Greg. I don't think it needs to go any higher than that. I think we got some very capable techie guys here. So great presentation, lots and lots of information there, very helpful information on all levels. And one other knob you could do is a more cowbell knob on the.
Yeah, that's true.
That would be good.
I mean, there's never a scenario where that's not going to work out.
All right, thank you so much, you guys.
Thank you.
Again, fill out that form, and then you can pick the subject, and we will bring in the experts. So if you have any kind of Sennheiser subjects that you want to bring up, we'll bring at least Rick back and maybe Greg. Who knows? You never know. All right,
Can't
thanks
keep me
so much,
away.
everybody. Thanks, guys. Have a
Thank
great
you.